Thank you very much, Mario. Welcome to my talk. So today I'm going to talk a little bit about our ongoing work on reinforcement learning, and specifically on creating some well-validated and benchmarked environments so that all of us can easily and without any effort in implementing CFD environments directly test and train the environment in reinforcement learning setups. So this work is a joint collaboration between the Aerodynamic Institute in Aachen, the Forschungszentrum in Jülich, as well as the University of Washington. And it contains contributions from Mario and Andy, who are our hosts here, and also from Miro, Matthias, Wolfgang, as well as Steve and me, who actually has the pleasure today to present some of our early results. So before we go a little bit into detail, let me quickly show you why we think reinforcement learning is a very promising direction in here we go. Why reinforcement learning is a very promising direction in future fluid flow control environments, and why standardized development efforts are so important for future enhancement in this field. So we all know that finding an optimal control policy is quite an important topic in our everyday life and can, for example, contain tasks like walking our legs or simply riding a bike. But it also is relevant for other examples like flight control, as we can see here, or also autonomously driving cars, which in the end ensures that we reach our destination safely. And more modern applications are, for example, human-like robots, as the one here from Boston Dynamics, or also in the context of aerospace, one impressive example, for instance, when SpaceX is landing their booster module. So this all includes finding an optimal control strategy, and most of this is done via model predictive controllers. However, there are some tasks which model predictive controllers cannot handle, since they are quite prone to uncertainties in real-world scenarios, and especially to unknown dynamics. And especially for this kind of task, reinforcement learning is a very promising direction, since it's offering a completely new level to match those kind of uncertainties which we are typically facing in real-world applications. And to show you that reinforcement learning has achieved some really cool results in the broader context of aviation and fluid mechanics, I want to show you one of my favorite examples from the University of Zurich, in which they demonstrate that reinforcement learning can basically achieve a superhuman performance in the incredibly challenging task of navigating a drone at high speed. And based on a training of 100 RL agents simultaneously, they managed to outperform current state-of-the-art model predictive controllers, as well as also current drone racing world champions. And the really cool thing about this work actually is that they only trained their RL agents on a standard laptop for 10 minutes and then unleashed it to a real world, and it still achieves a very impressive result. And of course, they also compared it to some state-of-the-art algorithms, which in their context is trajectory control and trajectory tracking and contouring control. And they found that the current state-of-the-art model predictive controllers barely reach a success rate of 20%. So in this context, the success rate means that so those algorithms only manage to fly through 20% of all gates of the circuit. While, for example, their RL agent always achieves a success rate of 100%, which is really cool. So what actually drives this kind of fundamental advancements in this area, as well as also in other very challenging real-world applications? And from our perspective, one of the major enablers for such kind of reinforcement learning enhancements or successes in recent years is the development of standardized and easily accessible environments that allow an entire research community to directly develop and train their agents on the same task. So famous examples are here on the slides. For example, DeepMind's Mojoko or StarCraft environment, or also the superfast Madrona engine project, as well as a little less famous example, which is more in our direction, the Fluid Lab, which basically imitates some everyday task in manipulating fluids. So it's a little bit inspired by computer vision, not really fundamental fluid mechanics. However, in our community, so for fundamental fluid mechanics, we currently do not have such kind of well-validated and broad, standardized and efficient environments, so especially some kind of collections, on which all of us can directly train and test our algorithm without actually worrying about the underlying CFD implementation or other important things like communicating between agents and environments or between agents themselves and whatever. And exactly this kind of lack of standardized benchmark scenarios motivated my colleagues and me to come up with a new benchmark platform. And this benchmark platform is then intended to actually bridge the world of reinforcement learning and the world of fundamental fluid mechanics. Because basically, expert in reinforcement learning or machine learning typically have a lot of trouble when trying to deploy their agents, their new enhancements in our community. They are definitely interested, but friends from Google and DeepMind tell me that currently for them it's too much effort to get knowledge and CFD and then try to use their agents in a physically motivated environment. So therefore, we decided that we want to aim that we aim to close this gap. And the first attempt we made in this direction was our Hydrogym project. So Hydrogym initially was designed to easily combine some flow environments, which we can see here with standard reinforcement learning agents for various tasks, ranging from active fluid flow control to smart sensor placement, as well as the optimization of some aerodynamic quantities. But before we go further into detail, let me quickly give you a very brief overview about reinforcement learning. In reinforcement learning, this is the typical setup we are usually facing. So in RL, we program an agent that interacts with an environment via an action, as you can see here. And typically, this, in our case, is some fluid flow environment. So in most cases, it will be some CFD simulation, but it could also be some kind of experiment. This is quite rare and new for this current state of the art, but I'm pretty sure in future we will also see more experiments. And the general setting for those studies is mostly identical. So we have an environment that is the fluid flow simulation, and then it computes the instantaneous flow field, for example, here around the cylinder with some vortex shedding. And then we extract some velocity or vorticity or also pressure values from this flow field at some specific locations. We can choose them. And then we forward this information to our agent. So then with this information, now our agent decides what kind of action it want to take. So this action in the end defines how the controller in the environment is actuated. And then the overall goal for our agent is to achieve the highest reward possible. So therefore, for every flow environment, we define an individual reward function, which, for example, for the current setup, could be that we want to minimize the drag and some lift fluctuations caused by the vortex shedding. All right, so so far so good. And So now let's come back to our hydrogym environment. And initially, we started with 4 different environments, including cylinder and cavity flows, as well as a fluidic pinball and a backward-facing step. And all of them have been implemented in an open source C solver, so a fire drake, which basically is well known for its nice and conveniently to use Python bindings, as well as their well-documented core functions. However, we quickly noticed that FireDrake also has some severe downsides for our project, since it is exclusively leveraging CPUs. And there are currently no efforts importing that to GPUs. And therefore, you basically can say FireDrake is mostly intended for small and medium-sized PDE problems. So as a result, we've been mostly limited to 2D environments, which already required a significant time of training efforts. For example, for larger problems, it was on the order of 2 to 3 weeks. So it was quite obvious for us that we need a more efficient CFD solver as a backbone for our RL setup, which in the end also allows us to leverage more recent, more modern hardware accelerators like GPUs. So therefore, we moved forward and created a highly efficient extension, which is called Hydrogym-GPU. And this is then intended to be well suited for both. On the one hand, the 2D toy examples we've seen before, and on the other hand, more challenging 3D applications, which then might contain millions of grid points and can also account for the very challenging turbulence-dominated flows we're typically facing in real-world application. So before we go on, please note that this is still ongoing work and we're heavily developing new environments. But today we want to share some of our early results with you, and therefore please think of everything I show you as kind of the beginning of the project rather than the end. All right. So similar to Hydrogym, we focused in the first step on re-implementing the original flow environment, but make them super fast and, for example, via GPU hardware, and extend them to 3D counterparts. And to do this, we switched to a new solver backbone, which is called Maya. And Maya is a recently open source high-performance PDE solver that is specifically designed for fluid flows. It has been developed at the Aerodynamic Institute in Aachen for more, and the Forschungszentrum Jülich for more than 10 years now. And basically, it's a C++-based code that can leverage CPUs as well as GPUs nowadays. And it provides interfaces for a lot of different solver types, so ranging from finite volume to, let's say, Boltzmann, and also more other couplers and solvers, including particle or also error acoustic simulations. So therefore, it was quite a natural choice for us to switch from FireDrake to Maya, as it is providing an immense flexibility in terms of future development, which nobody currently has explored in our community. Right, so now let's have a closer look to the environments which are part of our current work. And currently, all environments have been implemented using the latest Boltzmann solver. So of course, we always start with the flow around a cylinder, since this is a very well investigated control case with lots of different and interesting studies reported in literature. And even today, new results are reported more or less every month, which show new details about this kind of flow control problem. So therefore, I guess we all agree that the cylinder flow should always be part of some kind of standardized benchmark scenario. And in our work, we provide validated environments for a Reynolds number range of 100 to 3900. And our main control objective here is similar to literature. We wanna reduce the drag as well as to stabilize lift fluctuations. And to do that, we implemented 2 different actuation schemes. One are counteracting jets, the other is a rotating cylinder surface. Right, and then We also implemented the fluidic pinball, which basically consists of 3 of those cylinders, which are stacked in a triangle, as you can see here. And here we also concentrate more or less on the same control objective, so drag minimization and lift stabilization. And here we cover a Reynolds number range of 30 to 150, which basically covers the most important transient dynamics of this flow case. And then we also played around with cavity flow at 7,500, which is exhibiting some shear layer instabilities, as you can see in the image here. And our main goal is to stabilize those shear layer instabilities via reducing the overall turbulent kinetic energy of the flow field, as well as to reduce the pressure fluctuations inside the cavity. And to do that, we positioned a jet upstream of the left cavity edge, and this works actually very nicely. And finally, we also worked on a backward-facing step at a Reynolds number of 3,500, where we want to minimize the reattachment length behind the step and use one jet upstream of the step to realize this. However, since Maya actually is intended to deal with more complex and more challenging and of course more computationally more expensive setups, we're currently heavily working on 3-dimensional counterparts, on which I want to focus a little bit more in detail today. So again, we start with a 3-dimensional counterpart of the cylinder flow and created environments in the same Reynolds number range, so ranging from 100 to 3,900. And currently, we focus on the same control objectives, so drag reduction and lift stabilization. And here we employ counteracting jets, one at the bottom and one at the top, which basically are in the 3D case elongated across the entire spanwise direction. However, in our implementation, we ensured that in the end, the final user can decide how many jets he or she want to use and how long each individual jet is elongated in spanwise direction. And then we also considered a slightly more complex setup of a sphere flow, in which we target also a drag reduction setup. And to do that, we distribute multiple jets across the entire body surface and then allow to control those jets individually or also in groups. All right, and of course, we validated our simulations and compared them to other studies in the literature. So for example, at a Reynolds number of 200, we use a mesh with 46 million cells and achieve lift and drag values which deviate only slightly from values reported in literature. And also with respect to the Strual number, we match the literature pretty closely. So the Strual number is based on the vortex shedding period here. And also for a Reynolds number of 3,900, we designed a mesh with 82 million cells and closely match the values reported in the literature. Right, the same also holds for the sphere flow. Here at a Reynolds number of 300, we again match those of the literature pretty well. Here we need a mesh with more than 120 million cells to achieve that. And however, for larger Reynolds numbers, we are currently investigating test case at 3,700. We currently are facing some deviations, but I'm pretty sure in the next couple of days, we will also have a mesh that works very nicely on this test case. All right, so one of the first questions we actually wanted to answer is what was all the effort we put in switching the backbones, the CFD soil was actually worth it? And the answer to that was pretty clear. So now if we compare some computational resources we required to train RL agents side by side, then for example, for a 2D flow at a Reynolds number of 200, we trained fire drag on 16 cores. So fire drag scalability is not super good, unfortunately. So we couldn't leverage more than 16 cores, otherwise the communication overhead was too large. Anyway, so for this test case, FireDrake requires for one episode 7 minutes, while, for example, our Maya code, which is running on one GPU, only requires 12 seconds. So we are orders of magnitude lower compared to what we have had before. Or when we consider a full training schedule, then FireDrake requires something like 2 days, while we only need 40 minutes for our Maya solver. And the same also is true for larger Reynolds numbers. So for FireDrake on 128 cores, one episode takes more than 3 hours, which basically means that we can't really train it efficiently for a couple of hundred episodes, which are typically required by reinforcement learning. While Maya only needs something like 36 seconds for one episode or 3.5 hours for an entire training schedule. And also for the three-dimensional flow at a Reynolds number of 200, we train Maya on, or we use 4 GPUs for the flow environment computation and need something like 28 seconds and a couple of days overall. So here we need to acknowledge this is no toy example anymore. So this are indeed 46 million cells. And for the larger Reynolds number, we have 42 minutes and almost a week in full training schedule, but we are pretty confident that we basically can reduce it. So for example, if we use more GPUs, then we can already reduce it to 50 minutes, and we're pretty confident with new architectures like the Hopper or the Blackwell chip said that we can push it down to 7 minutes, and then it's very conveniently to train also larger meshes. And one important question actually was how can we achieve such kind of speed up? Of course, Maya actually is designed to support high performance computation. So it was designed to run as fast as possible. And the second aspect was we developed a new interface based on a new MPI interface, which is communicating between the RL agent and the flow environment to make this kind of communication super fast. So many applications in the fluid dynamic community currently use some I/O protocols, which are quite a bottleneck. So therefore, we wanted to make sure that our implementation is as fast as possible. And to do that, we leverage MPI's multi-program, multi-data interface, so basically MPMD. And using MPMD, we create for each agent and each flow environment an individual communicator group. And then in each of those groups, we can have a different number of GPUs. This can be chosen individually. So for example, for an agent, we typically only require 1 GPU, but for future model-based RL agents, we also can use more than 1 GPUs. While, for example, the Maya environment always uses 1, 4, 8, 16, you name it, GPUs. Which is working on, and this inter-GPU communication is then handled by the original MPI interface provided by Maya. So in the simplest case, which we can see here, we have 1 agent and 1 environment, which are communicating via this MPI protocol. And then we can also switch to more complex setups easily, so without actually changing anything of the code, but a few lines in the configuration setup. So for multi-agent reinforcement learning, as Ricardo showed a couple of minutes ago, we can directly create more environments and more agents simultaneously. And we can easily control how they are communicating with each other with barely any loss of performance, which basically I think is really cool. And one other nice thing is that we actually don't need to worry about things like gradient sharing or weight sharing, because basically we can leverage natively supported libraries like NVIDIA's Nickel protocol, which takes care of that. So we there also ensure that we don't have any kind of lost performance. And in practice, we tried this on 8 reinforcement learning agents communicating with 8 different environments, and this works really nicely. And we can also create more exotic configurations like this one. So we have multiple agents working with one environment in the end, again, without changing anything of the code, just a little bit in the configuration file. This is often used in some large-scale offline reinforcement learning applications when the environment is super cost intensive, or the other way around, if we have multiple environments communicating with one agent. So I think this is really cool, and I think this kind of flexibility and scalability is a key advantage of Hydrogym-GPU, and it might also be quite interesting for some of our community here. Right. So far, so good. So now let's have some look at results we've generated so far. So unfortunately, we haven't had time to benchmark all results right now. But here I want to share some exemplary results, which mostly cover the cylinder flow right now. However, I know these results are not super exciting. The cylinder flow is not super exciting, but these will give you a very good intuition what hydrogen actually will be capable of and what you can use it in the end for. All right, so let's start with some results on a 2D cylinder flow, where we investigate a Reynolds number of 200. And here I plotted the reward, the lift fluctuations, as well as the drag, and also a vorticity field at the bottom. And we can see that we trained 3 different agents. So one on policy, which is PPO. So basically PPO is used for more than 90%, I would say, in the fluid community. And then also 2 off-policy agents, DDPG and TD3. And in all cases, the agents learn a control policy that stabilizes the wake and mostly also reduces the lift fluctuations, which are caused by the vortex shedding. So all in all, most of the agents achieve a drag reduction of 12%, which matches closely reported values from the literature. And if I plot now all agents in one figure, then we can see that they mostly perform equally, especially when we've reached the final state. So there are barely any differences. Especially here for the reward, as well as also for lift and drag values. But this was kind of expectable because actually many other researchers already have shown that those agents work very reliably on a cylinder flow. However, it is still nice to see that Hydrogym-GPU directly works out of the box for those test cases. And again, I want to stress that this was only a training of a little bit more than half an hour. So then the next step we wanted to investigate was actually, can we use those control policies we trained in a 2D environment and transfer it to a 3D environment? And we've done that, and this actually worked surprisingly well. And so basically here, I'm showing results of a 0-shot transfer learning experiment, which basically means we directly pick the control policy trained in a 2D environment and immediately apply it to a 3D environment. And here we can see that we don't reach the same performance as the original one, which is quite obvious, but we still reach a very useful drag reduction of 7 to 8%, which actually without actually training a single step in the 3D environment. And of course, then we wanted to know if we can extend this kind of setup and therefore use the fine-tuning setup. And here we can see that we've trained them the 2D policy in the 3D environment for 20 episodes. And then we can observe that we are almost matching the original case of the 2D flow environment, which I think is pretty nice because it's a very promising future direction to train in very cost-efficient environments and then deploy it and fine-tune it in more costly 3D environments. So basically here, we only required 10% of the original cost when we only train in 3D environments and almost achieves the same results. And finally, I want to show you some results of multi-agent training schedules. So on the left side, we see the total reward over each episode during training for a single agent setup. And on the right side, we see one for multi-agent reinforcement learning, which basically uses 8 agents trained on age environments simultaneously. And overall, we can see that this multi-agent RL setup converges faster and only requires approximately 50 episodes to reach the final state, while the single agent requires something like 75 to 100 episodes to reach the final state. And of course, you can say, yeah, this was kind of expectable, but for us, it was quite nice to see that also this multi-agent training immediately works and is super fast without barely any kind of performance loss. All right, so that's it from my side. Let me finally quickly summarize my talk. So today, I talked a lot about our ongoing work on Hydrogym-GPU, which is intended to provide an easy, accessible, and validated benchmark collection so that all of us can easily and conveniently test and train our agent without actually worrying about anything of the underlying implementation. So therefore, we leveraged the Maya CFD solver, and doing so, it allows us to use Hydrogym-GPUs on both on CPUs as well as GPUs immediately. And it also provides a standard gym-like IL interface, which is pretty important for the machine learning community, because basically they can immediately hook up their agent on that. And we also ensured that we can use Hydrogym-GPU directly for the small test cases on a standard laptop, so I can train it on my own. A notebook requires something like an hour, but it also is well suited for HPC clusters, which in the end will drive our main applications in the future, so more challenging 3D applications containing millions of cells. And moreover, we developed a new MPI interface, which is based on MPMD, to enable a direct communication between the agent and the flow environment, which makes it super fast. And therefore, we can also directly switch between single and multi-agents with barely changing anything in the code. And finally, I also briefly discussed that Hydrogym-GPU also supports transfer learning tasks from 2D to 3D, which could in the end drastically reduce the computational effort we need to find new control policies in more challenging flow cases. And in future, we will work on a variety of new environments and new flow types, which go far beyond the current state we are currently having, especially with respect to more challenging flow types like multi-phase flows and compressible flows, because all of this is supported by the Maya solver, and it offers us an immense flexibility and variety of future environments, which we can all embed in this kind of Hydrogym-GPU benchmark. All right, so that's it from my side. Thank you very much for your attention. And if you do have some questions, please reach out.